So hi everyone, my name is Mingxun Zhou. I'm a PhD from CMU. So today I'm going to talk about the power of the differentially oblivious shuffle model in distributed privacy. And this is a joint work with my advisor, Elaine Shi. Okay, whatever. So as we all know that in differential privacy, we have the central model. So basically, the central server is trusted, and every client can directly send their raw data to the central server. And the central server can do whatever it wants. For example, it can run some machine learning and it uses a privacy protection mechanism and output some useful statistics, something like that. And we also have the local model, which is protect more privacy. In this model, the central server is not trusted, and every client needs to protect their own privacy. So they need to run some local randomizer, sometimes called a privacy-preserving encodings, and they send the encodings to the server, and the server needs to, based on those privacy encodings, and calculate some useful statistics. In the middle ground of local and central model, there is a shuffle model. So right now, the central server is still not trusted, but now we have a shuffler that is trusted. So every client can, encode their local data and send the encodings to the shuffler. And the shuffler will shuffle all those messages and output the randomly permuted message set to the server. So basically, the server sees a bunch of anonymized messages. And the good thing is, shuffle model often achieves fundamentally better privacy utility trade-off than local model, and often it provides a stronger privacy definition than the central model. Implementing anonymous communication, or in our case, it's just the shuffler, is a classical and long-standing problem in cryptography community. There are some previous constructions like MixNet, DCNet, Tor network, multi-server systems, something like that. But the problem is implementing a secure shuffler is not that easy. For example, in the P2P setting or in a single server setting, generally it has high overhead. For example, we have n clients and each client wants to send one message. Then the total number of messages would generally be quadratic, which is not good. In the multi-server setting, well, the solution is more efficient, but we do need more trust assumption. For example, we assume those servers don't collude with each other. So this is a very strong assumption. And to avoid those drawbacks, we want to relax the definition of the shuffler. The relaxation here, we have differentially oblivious shuffler, and the functionality of DO shuffler is still the same, that it outputs a random permutation of those messages. But right now, the privacy guarantee is not fully secure, that we allow some kind of DP leakage. And the natural question to ask is how to define neighboring input in DO shuffle. So here's the definition. So now we have 5 clients, and every client has one message. In the neighboring case, basically a pair of clients will swap their messages. So based on this case, we require that, so generally we implement a DO shuffle with a distributed protocol, and we assume, for example, some client could be corrupted and also the server is corrupted. We require that if one pair of messages is swapped, then we execute the protocol, then the view of the adversary needs to be epsilon delta close. So this is a definition of differentially oblivious shuffle. And this kind of definition provides some deniability for the sources of the messages. So intuitively, because we have some anonymity guarantee for the messages, so we still have some privacy amplification for the clients. A DO shuffle is asymptotically cheaper to realize than a fully secure shuffle. There are already 2 constructions for DO shuffler. The one is using onion routing, another one is non-interactive matrix shuffling. The good thing is the total number of messages in both of the constructions is only quasi-linear, which is n times polylog n. So it is more efficient. So now we really want to know that can we match shuffle model result with a deal shuffle? So remember, deal shuffle is a relaxation of the perfect shuffle. And the answer is yes. Here's our main result. We have an optimal privacy amplification in single message deal shuffle model. I will explain what is privacy amplification in the next slide. And we have some, we explore some multi-message deal shuffle model protocols. We study the problem of histogram and real summation, and we have some very good protocols out there. So what does it mean by privacy amplification by shuffling? Here's a statement, a theorem, a very, very great theorem proved by Feldman, Mellon, and Tawar. Tawar is actually here. So it says for any epsilon naught LDP randomizer, and you plug that into the shuffle model, and let's assume the shuffler is a perfect shuffler such that it leaks no information. Then the composition mechanism is an epsilon delta DP mechanism where the central epsilon is much smaller than epsilon 0. So in some sense, the privacy is amplified. Let's take a look at an example. So let's say your local randomizer has epsilon naught equals to 1. Then you plug that into the shuffle model. And in the shuffle model, it has much better privacy parameter. Here, epsilon is roughly √3 divided by n. So if you have like 10,000 clients and you're in the shuffle model, your privacy is very, very good. And now we prove that this privacy amplification still holds under the deal shuffle model. So right now we don't have a perfect shuffler, but we have an epsilon 1 delta 1 deal shuffler against T-corrupted users. Then the composition mechanism is an epsilon plus epsilon 1 delta plus delta 1 DP mechanism, where here the epsilon is roughly the same as the previous privacy amplification result, except that now we are divided by n minus t because we have T-corrupted users. So we actually match the previous results. So now I'm going to talk about from the high level how we prove this result in deal shuffle model. So what we really want to prove here is that now let's fix two neighboring inputs, x and x prime. So x means, for example, the Iron Man would have input A, and everybody else has input x2 to x5. And in the neighboring case, the Iron Man would have input B, and everybody else has the same inputs. And they would use the local randomizer, and then they participate in the deal shuffle. And we want to prove that these two cases should be differentially private from the view of the adversary. A formal statement here. Mx is defined by the set of the messages sent to the shuffler given input x. So basically, those clients involve the local randomizer and they generate a bunch of messages, and the set of the messages is mx. And mx prime is similar, but it's for the input x prime. And already the privacy amplification theorem of perfect shuffler already shows that these two random variables are epsilon delta indistinguishable. So our goal is to prove that the view of the adversary during the execution of the deal shuffling protocol S, given input x or x prime, is epsilon plus epsilon 1 delta plus delta 1 indistinguishable. So notice that the view here actually includes the output of the shuffler. And it is actually sufficient to prove that condition on the set of the messages sent to the shuffler, the view of the adversary is actually epsilon 1 delta 1 closed. So let's take a look at an example. For example, condition on m equals to 1, 1 to the 2. That means the messages sent to the deal shuffle is 1, 1 to the 2. And the clients invoke their local randomizer. And in the first case, they generate a bunch of messages like 1, 2, 1, 2, 2. So after permutation, the set will be exactly 1, 1, 2, 2. And in the second case, let's say they generate some messages like 2, 1, 1, 2, 2. And let's take a look at these two cases. We realize that the first two clients exactly swap their messages, right? And then the deal shuffle ensures that these two cases are epsilon1, delta1 indistinguishable. So the key idea here is to find a bipartite graph matching. So we condition on a message set M 1, 1, 2 to 2. And for all possible message sequences, they could all appear with some probability. So what we really need to do is find the bipartite graph matching phi from permutation, all permutation possible sequences M to another sequence. And what we really need is that M and phi M should be neighbors in deal shuffle. That means a pair of clients swap their inputs, and they should have matched conditional probability. I will talk about that in the next slide. So let's take a look at an example. So let's see, let's say the permutation of M only includes like 3 possible message sequences. And let's say in the first case, the conditional probability of each message sequence is 1/3, 1/2, and 1/6. And they are UV double. And when the input is X prime, the conditional probability of UVWs will be 1/2, 1/3, and 1/6. And then what we have is that U and V are a pair of neighbors, and because W and W, they are basically the same thing. So we also assume that they are a pair of neighbors. So we can simply find a matching like this. Now you can see that they have the matched conditional probability. And using this matching, we can very simply prove that the view of the adversary condition on M, given the input is X, is somehow a linear mixture of those distributions. That is the view when given the input message sequence U. And you can see here, it's actually a linear mixture of those distributions. And we directly use that matching and jump from this line to the next line. And as you can see, the third line here is exactly the linear mixture distribution of the view of the adversary given input X prime. And then we're done. So as you can see, if we can find some matching like this, then we're done. We can prove the theory. Unfortunately, finding such matching is not easy. And we really need some special structure in the previous privacy amplification proof. So here's the key idea from the privacy amplification proof in the perfect shuffle model. So for any X, for any input X, if the local randomizer epsilon, local randomizer Rx, it is an epsilon naught LDP randomizer, then it can be seen as a mixture distribution of the following 3 distributions. So it can be decomposed into RA, and RA appears with probability e to the negative epsilon naught divided by 2, and RB with the same probability and some leftover distributions. So this is guaranteed by the definition of epsilon naught LDP randomizer. The message here is that with probability e to the negative epsilon naught, regardless of the input, the randomizer will sample from RA or RB. So basically, in some sense, with the probability e to the negative epsilon naught, we only care about RA and RB, and we don't care about the leftover. So using this decomposition, we can rewrite the output distribution. We decompose Rx2 to Rx4 here, let's say. And here's the key idea number 3. So actually, the previous privacy amplification proof provides a stronger corollary that even given some auxiliary to the adversary, the mechanism is still private. So the auxiliary information here includes the exact messages from the client sampling from leftover distribution. And the intuition here, client 1's message. So client 1 will sample from RA or RB because that's in the neighboring definition. So client 1's message is actually hiding among many clones of RA and RB. And this is the result why their paper is called Hiding Among the Clones. Blah, blah, blah. So visualizing the auxiliary information gives something like this. So we decompose Rx2 to Rx4. And for example, in some case, we know that Rx2 is going to sample from RA or RB. And Rx3 is going to also sampling from RA or RB. But for Rx4, it's not going to sample from RA or RB. It's going to sample from the leftover distribution. And it's definitely going to sample from message 2. So condition on this auxiliary information, client 1 would definitely sample from RA. Client 2 and 3 would definitely sample from the linear mixture of RA and RB, and client 4 exactly output message 2. So as you can see here, after conditional auxiliary information, we no longer care about the leftover distribution. So using this very good property, after condition on the auxiliary information, we only care about the 3 types of distribution. And now the whole structure of those distribution is much more clear, and we can use a split and match trick from another paper to prove some matching like that can exist. And after the matching, we can apply some standard DP composition technique. So that's how we prove it. We also study some multi-message DO shuffle model protocols. And the definition in multi-message is basically the same, that a pair of clients swap their messages, but right now every client could submit multiple messages. And in the multi-message model, we have a protocol that is actually from the some previous paper, and we proved that protocol is actually still private under DO model, and the communication is roughly polylogarithmic. The error is also polylogarithmic, and there's actually a lower bound for single message model that is actually n to the one quarter. That means we can break the lower bound for a single message model using multiple messages. And that's roughly the same for real value summation. We have a protocol that uses log n messages, and the error is log n squared, and we still break the lower bound for a single message model. But this is actually not, not optimal. The best shuffle DP mechanism can use 1 plus small o1 messages, and the error is roughly polylogarithmic. So we are trying to compile that mechanism into our model. So here's a summary. DO shufflers are cheaper than superior shufflers, and many shuffle model results can still hold in DO shuffle model. Future work, we would like to study a richer class of tasks. We would like to know if there's any theoretical separation between DO shuffle and shuffle model, and want to practically implement the DO shuffle and also those distributed private protocols. All right, thanks.